All right. Thank you so much for tuning in to the Statistics for Data Science workshop for the Data Science Student Society. I'm Igor Prelov, and I'm presenting alongside Ethan today. And so, yeah, we're excited to get started.
Yeah. All right. So let's just get into it. So why would you want to use statistics for data science? Well, statistics and statistical tests allow data scientists to make predictions from an analysis of data. And this has many applications, right, in many fields of data science, including classification, artificial intelligence, data visualizations, trend spotting, and telling if data and results are significant. And without statistics, most data scientists wouldn't be able to make any inferences or provide any valuable information to their companies or organizations. There would be no point of data science if they couldn't use statistics to make inferences from the data.
All right. So, a great way to dive into some of the nitty-gritty of statistics is actually looking at some probability distributions. And the way you want to break down different kinds of probability distributions is looking at their probability distribution functions. That's essentially what defines the distribution itself. You'll often see these referred to as PDF, as you can see in the slides. And essentially what the PDF describes, it's all the possible values or the probabilities that a random variable can take within a range of possible values. So it's literally just a function that assigns probabilities for certain inputs that you give to the function. It has some key properties, as you can see. The probability distribution function must give a value between 0 and 1, and the sum of all the probabilities must equal to 1. And this kind of, if you just think about it logically, this checks out. If you flip a coin, for example, it's going to be a 50% chance you get heads and 50% chance you get tails. And those are your only two outcomes. They sum to 1. And of course, both of the outcomes have probability between 0 and 1. And this must be true for any kind of probability distribution function. Now, PDFs can describe either discrete or continuous settings. Discrete would be something like I mentioned, like flipping a coin or rolling a dice, where it's not continuous. You have specific probabilities at specific values. The PDF will actually give you a concrete value for a certain outcome. Whereas for a continuous probability distribution function, it's quite literally occurring in a continuous sample space, and oftentimes you'll see these modeled with integrals and derivatives. You have to use some calculus with continuous PDFs. Some examples of common probability distribution functions that are often used to model different events in the real world. For discrete, we have functions like the Bernoulli, the binomial distribution, the Poisson distribution, and for continuous, you have things like the Cauchy and the normal continuous uniform. So I'm going to dive a little bit deeper into some specific kinds of distributions. First off, we have the binomial distribution. So as mentioned on the previous slide, it's a discrete probability PDF, discrete probability distribution function. The way to think of this is that it's counting the number of successes over n independent trials, with each event, with the successes having probability p. So again, it's the number of successes, predicted number of successes over n independent trials with probability p. Independent just means that each trial has no effect on another trial. So for example, flipping a coin, each time, whether you get heads or tails on the current flip doesn't affect what you're going to get on the next flip. An example would be, say you're flipping an unfair coin with the probability of heads being 1/3. We can model how many heads you're expected to get over 100 coin flips by using a binomial distribution, how many quote unquote successes you're going to get over 100 coin flips. You have this formula here as well. This is the probability. So probability of x equals k. So probability that you have k successes. We have the binomial coefficient n choose k times the probability. Of course, you're going to have to get k probability k successes, so probability of getting k times itself, k times over, and then the probability of not getting a success, n minus k times over. So that's the binomial distribution. You'll see it quite frequently, and one that's closely tied to that is actually the Poisson distribution. It's it's essentially modeling the binomial distribution, but it's used specifically to describe rare and independent discrete events in continuous space and time. So just to give this a definition, it's the distribution of the number of events within a time period when you know the average number of events in that time period. And we have the formula as well. Lambda, as you can see, lambda just stands for the average number of events in the time period that we're given. And then k is same as k is above. It's the k events over a period of time. These are often used in settings where we're trying to, like I said, model how many events or occurrences we have over a period of time. For example, you could think of customers arriving at a cafe between 7 and 9 a.m. If you knew, for example, how many customers on average arrive over an hour or over half an hour, then you could use the Poisson distribution to model this situation. All right, and so applying these distributions and these distribution functions, we actually get to statistical hypothesis testing, which is a useful tool for actually interpreting results in the data sets you might be working with in data science. It's a good way of telling how meaningful are the actual results that you're collecting from your surveys or experiments. A way to think about this, how statistical hypothesis testing works, is that you essentially have to figure out, you look at your results and you figure out the likelihood that you could have obtained your results by random chance. And the higher the likelihood that you could have gotten your results by random chance, the weaker the results are. So to get into some of the details, you first need to define your null hypothesis and your alternative hypothesis. The null hypothesis is the hypothesis you hope to reject or disprove using the data or the experiments you've collected. And the alternative hypothesis is, it's the opposite, it's quite literally the opposite of the null hypothesis. It's what you're hoping to prove using your statistical test. Now, we're going to go over a couple different statistical tests. The point is that each one gives you a different test statistic. And then you use this test statistic in comparison with what's called a critical value. Oftentimes, this critical value will be 0.05. And you're going to use this to reject or not reject the null hypothesis based on a comparison.
All right, so one of the most common statistical tests is the z-test. And the way that this test is done is by using a normal distribution to determine how likely a result or outcome is. So a normal distribution is a very common distribution that's found in many natural phenomenon, right? Like the most classic example is either like height or like weight or something for a population. Those both follow normal distributions. And given a mean and a standard deviation, where the standard deviation is like how far away, like on average, things are from the mean, right? That's a very like rough understanding of it, but it'll do. What's it called? It allows us to make inferences about how likely that a certain like occurrence was to have happened. So like a certain weight is given that the population has this average weight, right? So using that, we can use this formula to find the z-score, which is a score that tells us how many standard deviations above or below the mean a value is, and that tells us how likely it was to have occurred. So the further it is from the mean, the less likely it is to occur by chance, and the closer it is to the mean, the more likely it is to have occurred by chance. All right, so we have an example here from our code, and let me just hop over to that. So in, what's it called, the Zoom chat, I've sent a link to the data set that we're working with here, which is the Pokemon data set, as well as this Google Colab notebook, which allows us to what's it called? Write some code here to analyze this data. So all you have to do is upload the files, import the libraries, and here is our data set. So it's a simple data set that has all the Pokemon up to like generation 8 of like the Pokemon games or something like that. And it has all of their stats. So their attack, their HP, all that sort of thing, as well as their types, right? And here, we're just going to do a small z-test on that. So what this z-test does is that it is a z-test for the total stat total of the Pokemon, right? So what it does is it finds the z-score of, let's say, a Pokemon that has a 700 base stat total, and it finds the p-value for that using this SciPy library called stats, which has some stats functions to model the normal distribution. So first we calculate the z-score, right? And then we plug that into the normal distribution, and we get that this with a z-score of 2.2, the p-value is 0.01. That means that if this was to have occurred by chance and it was completely random, there would only have been a 1% chance that it would have fallen where it did, which means that this Pokemon with a 700 stat total was probably not randomly chosen from the, what's it called? From the distribution of all Pokemon, because that's a pretty low total.
All right. So I wanted Ethan mentioned the p-value just now, and I wanted to just explain a little bit further how exactly you interpret this p-value. You can think of it as evidence against the null hypothesis. The smaller the p-value, the stronger the evidence we have of rejection. It's if you look at the distribution to the right, we have the sort of bell curve, and we have the critical value. The p-value is all the area under the curve to the right of the critical value. So that's just a little bit of intuition is what it's actually telling you. It's the probability of observing a result at least as extreme as the critical value. And as Ethan mentioned, in this specific example, the p-value is 0.01. And indeed, it is the p-value is less than or equal to 0.05. We're able to reject the null hypothesis, whatever it is. In this specific situation, basically, it's telling us that there's a, like Ethan said, there's a very low chance that we observed the outcome purely by chance. So, all right, on to the next test. Okay, so we're going to talk about the chi-squared test. Next, it's a little bit more of a niche statistic. You use it in situations where you need help deciding whether or not a relationship exists between two categorical variables of a population. So categorical variables are non-numerical data usually, and so for example, this could be for perhaps height and weight of a population. We could run a chi-square test on this data, and that could give us tell us whether or not there's some kind of relationship. As you can see, these are in the graph we have the chi-square distribution changes based on the amount of degrees of freedom you allow. So the greater degrees of freedom, the more and more it starts to look like a normal distribution. And in our specific example that we're going to show next, we're actually going to show a one-way chi-square test. So what I did was pick just one categorical variable out of a data set, and basically compare that to a completely uniform distribution of those categorical variables. You can think of testing the data's goodness of fit with our theoretical expectations of the distribution. So if you want to show the code for the chi-squared test. All right. Yeah, so I pulled out using some NumPy libraries. I pulled out the type one column from the data frame above. If you want to just show that real quick, it's basically just all of the different types. Yeah, all the different kinds of Pokemon. We have grass, fire, psychic, etc. All right, and if we go back down, we're going to basically we've created this array, this list tally, and then we're gonna loop through it and zip to kind of create a tuple between unique and count. And we have the printout on the bottom there for you to kind of just give you a visual of what the basically this is tallying up how many bug types we have, how many dark types we have, how many dragon types, etc. over the, I believe, 800 Pokemon in the data set. And now I'm looping through, I created another list, and we're gonna basically just extract all the counts for each type. And I've printed out the counts below on the second line as well. And then I simply just use the stats library to run a chi-square, a one-way chi-square test on this list of counts in the second line. And as you can see, it's not a very meaningful statistic. It's a very small p-value, but so probably could have chosen a kind of a more relevant data set to work with, but this just gives you an idea of what the actual application of the libraries looks like when you're doing a chi-square one-way test. All right.
All right. And finally, to close this off, let's talk about ANOVA test. So an ANOVA test is very similar to a chi-square test in that it's looking to see if there is a difference between these groups and if all the groups came from the same distribution, right? So if they were all like uniform, they all had the same mean, right? And that's what an ANOVA test. However, the difference between this and a chi-square test is that this is looking at a certain what's it called? Mean, right, of each group, instead of looking at the counts of each group. It's looking at the values of each group. So it's looking at a quantitative variable instead of a just the counts, right? And so it's done by you take the sum of like all the variances of all the groups, and then you divide that by the total amount of values in each group. And obviously you divide by the degrees of freedom to account for like the different numbers of groups and all that sort of stuff. And that gives you an F score. So an F score is like a Z score, or like the chi-squared test, chi-squared value, in that it's the result that you get from performing the statistical test. And by looking at the regular distribution of an F distribution, you can tell whether or not this result was likely to have occurred by chance or not. So yeah, so if you can see here, we don't have to go over to the other to the notebook because I put it right here. But as you can see, this is what an ANOVA distribution looks like, right? And this F value gives us the probability that this was to have occurred just purely by chance, and they all came from the same distribution, if they all came from the same distribution. So if you look at the code, what I do is I take the attack and the type, the first type of each Pokemon, and then for each type of the first types, I add all the values of attack for each Pokemon that has that type to a dictionary, right? And then I plug each of those lists of values of attacks into a F test, a ANOVA test, right, using the stats library. And that gives us a statistic of 6.06, which is very high for this sort of distribution. And you can tell that by the p-value, right? So the p-value is very low, which means that this probably didn't occur by chance. It probably wasn't that every single Pokemon got the same attack, and it just so happened that, what's it called? They got sorted into these groups like that. So there probably was something by the game developers to give certain types more attack, right? So that's how we can tell by this low p-value. All right, and yeah, I think that sort of concludes our presentation for today. And if you guys have any feedback, anything you want to tell us, you can scan this link here, fill out the form, And yeah, I believe there's a raffle that if you fill out the form, you can win.
Oh yeah,
Do you know anything about that, Igor?
yeah. Yeah, if you fill out the feedback, you are entered into a raffle. You'll find out by the end of the academic year, I think. I don't remember what's in the raffle, but it's some good stuff as far as I remember. Yeah, it's like it's not just like a bag of chips or something. Um, anyway, yeah. Thank you guys so much for coming and listening, whether or not you watch the recording. Yeah, thank you, Ethan, and I hope you guys have a wonderful rest of your day.